Welcome to this video where we're going to estimate a population mean. And we're going to estimate it from a sample. We're going to take a sample and have the sample mean. But our estimation for this section and the formulas that we have here only works if we have a population standard deviation. We'll have other formulas in other sections if we do not have a population standard deviation. So the idea here is that we go out to the pond and we catch 20 bass, and the average length of those from the sample is 6 inches. Okay? And we'd like to come up with an estimate, which would be a range, since it's an estimate, for the actual mean of all the bass in the pond. Okay, so hopefully we're coming up with an interval or a range that the actual true mean would be within. Okay, so to do this, we're going to need a population standard deviation, which would generally come from a separate study, something we could either borrow from another study or maybe it's known from different experiments. But we could use an example here if we want to find the range for the length of bass in our pond. We might use the standard deviation for the bass in the state or maybe even a region, something that seems applicable. And we're also going to have a confidence interval, which tells us how well our estimation is. So here's a question. It says, a company that produces white bread is concerned about the distribution of the amount of sodium in its bread. The company takes a simple random sample of 100 slices of bread and computes the sample mean to be 103 milligrams of sodium per slice. Now that's from the sample. It says we're going to construct a 99% confidence interval for the unknown population mean of the sodium level that the and we're going to assume that the population standard deviation is 10 milligrams. Now that could have come from other bread that we work with or another company or maybe a different day. Okay, but this is given to us as a population standard deviation. So what I was given, we were given a sample size of 100. Remember this sample here, it means sample mean of 103 milligrams. This here is the symbol for population standard deviation, which was 10 milligrams. And this C is a new notation, but it's going to represent the confidence level. In this case, it would be 99%. That's given in the problem. What we're looking for, if you remember this symbol, is the population mean. So to talk a little bit about a confidence interval. Okay, so that's the notation we said was 99%. We're using C to represent that. That means that we want to create an interval, a low point to a high point, that we would assume that the actual population mean would be in. Okay, and we would have 99% certainty that it falls in there. We can change that percentage in the problems. Okay, but what it means is the more confidence you're going to have in your interval, probably the larger the interval is going to be. The more effort you put into trying to guarantee you have the population mean, the more you need to be able to accept variation. So the larger the percent here, the larger the interval will be. So what do we do with C? Okay, well, C is kind of converted to a z-score, but you won't use the regular z-score table unless you really want to do a lot of work. Okay, but this should be on your z-score table. If not, I've provided it separately. But over here you see the level of confidence, and over here you see what they call a critical value, or, and this is not a z-score, but it's a range of z-scores. So for our 99%, we're going to use z of 0.99, and this is the notation you would use. And from the table, it's 2.58. Now what that means is that we're trying to center 99% of the data. So we're not taking the first 99%, which means the left-hand side. We're not taking the right-hand side 99%. We're taking the middle 99%. If you were to take these and look them up in the table, you could take the left side, the right side, and if you actually got the probability and subtracted them, they should be very close to the 0.99 probability. So when you're given a confidence level, all you have to do is come look it up and get the z-score. Okay. So now we want to actually calculate the confidence interval. Now it looks kind of scary here. There's two versions of the formula, but let's explain the first one here. So in the middle we're trying to find the population mean, and we said we're going to have a range. So there's going to be a value below it and a value above it, which means hopefully our estimation will fall somewhere between those two numbers. And everything you see here you would have to have given to you, which we do. Sample mean, the z-score for the confidence interval that we just looked up in the table, the population standard deviation, and the sample size. Now here's a simpler version, but you still have to calculate what E is. And E is the margin of error. So if you notice the formula here for E, this little doodad is right here. But sometimes you may be given a margin of error, so it may save you a little bit of trouble. But if you're ever asked to calculate the margin of error, notice that you've probably done that if you've already calculated an interval. So back to our problem. We plug everything in. The nice thing about this one is 10 over the square root of 100 is 10 over 10 or 1, so that just kind of falls out. But here's the margin of error for this problem. It's just coincidence that was the z-score we used. Okay. But it gives us a range on both sides. Here we subtract that error. Here we add that error. So what we have here is we believe that the population average of sodium in all the white bread is somewhere between 100.42 milligrams per slice and 105.58 milligrams per slice. And that's with a confidence level of 99%. And here I just stole some thunder. But if you want to change the confidence level, you could. That means if you change this confidence level to something less than 99%, you would have a smaller interval, but you could actually miss the real population mean. Two things that can give you a better estimate would be a larger confidence level and a larger sample size. Remember, sample size, the larger it is, the more accurate you would be. So here's a second example. It says, efficiency experts study the processes used to manufacture items in order to make them as efficient as possible. One of the steps used to manufacture a metal clamp involves the drilling of 3 holes. In a sample of 75 clamps, the mean time to complete this step was 50.1 seconds. Assume that the population standard deviation is 10 seconds. Okay, so that's a pretty big standard deviation here. Okay, so this 50 seconds can vary a good bit based off of that. Okay, so it says estimate the population mean using a 95% confidence interval. So once again, all the givens here, sample was of 75 clamps. The average of that sample was 50.1 seconds. The standard deviation for the population that was given is 10 seconds. The confidence level is 95%, which when we look that up to get a critical value in that table was 1.96. We plug and push. Make sure you're getting all this in the calculator correctly so that you can get these values. But the time should be between 47.837 seconds and 52.363 seconds. And that's with 95% confidence. So there's still a small chance that the actual population average is outside of that interval. Okay, but it is an estimate. Okay. One other thing you might be asked to find here is if you're giving a certain amount of error that's acceptable, to figure out what the sample size you would need to look at to see if you meet that. Okay, so here's a question. It says a soccer ball manufacturer wants to estimate the mean circumference of soccer balls within 1/10 of an inch. What that means is they're allowing for 1/10 of an inch of error. Okay, so we need to figure out how many soccer balls we should look at if we're going to construct an 85% confidence level. Okay, and we need the population standard deviation, which they're giving us as 0.25. This formula can be reworked from the other one, but you see all the things here. The error was given, which if it wasn't, we could calculate it from other places, but you kind of need sample size. Here's our critical value, here's our population standard deviation, all that needs to be done and then squared. So here's all the items we were given. Confidence level at 85% gave us a critical value of 1.44. Push, make sure with your calculator you get what you want here. Here with n, since n is a sample size, that should be a whole number. And you should always round up if you don't get a whole number, because you can't have 12.96 soccer balls. Okay, and if you had 12 soccer balls, the error would not be within that range. So round it up. It'll give you a little bit of extra wiggle room, but it'll give you a whole number which will make sense. Okay, thank you.